If you've done any data science or machine learning in Python, there's a really good chance you've used NumPy, maybe without even knowing it. It's like the bedrock, the foundation that pretty much the entire Python data science world is built on. So today, we're going to dig into what makes NumPy so critical and really how it lets you write code that's not just cleaner, but way faster. Let's jump in.
All right, so here's our game plan. First, we'll cover why NumPy is such a big deal. Then, we'll put Python lists and NumPy arrays head-to-head to see the real differences. From there, we'll take a look at the anatomy of an array, figure out how to create and shape them, and then get into the real secret sauce, vectorization. And to wrap it all up, we'll get you started on your own.
Okay, so let's really set the stage here. Thinking about learning NumPy, it's kind of like learning the alphabet before you learn to read. It is the fundamental language for doing data science in Python. Seriously, it's not just some other library you can choose to use or not. It's the engine, the core machinery that makes doing heavy-duty math in an easy-to-use language like Python actually work.
And this quote just hits the nail on the head. I mean, think about the all-stars of the Python data world, right? You've got pandas, scikit-learn, matplotlib. Well, if you could pop the hood on any of them, you'd find NumPy is the engine powering the whole thing. They are all built right on top of it. They completely rely on NumPy's super efficient arrays to do all the heavy lifting. That column in your pandas data frame? Yep, that's just a NumPy array with some extra bells and whistles.
Okay, check this out. This really shows you the difference right away. On the left, you've got your standard Python list. To double every number, you write a list comprehension. You're basically telling Python, hey, go through every single item one by one and multiply it. And that works, it's fine. But look at the right. With NumPy, you just take the whole array and multiply it by 2. That's it. It's so clean, so readable, but here's the kicker. It's not just about typing less. That simple line of code on the right is going to run circles around the one on the left. We're talking a huge speed difference.
So let's dive a little deeper into that idea and really compare these two things side by side. Once you get this difference, you'll understand exactly why NumPy even exists.
Okay, this table lays it all out. The key thing with Python lists is their flexibility, right? You can throw anything in there, numbers, text, whatever. But that flexibility has a hidden cost. See where it says scattered memory? That means a list is basically just a collection of signposts, or pointers, each pointing to where the actual data is stored all over your computer's memory. It's kind of disorganized. NumPy arrays, though, are strict. They say, nope, everything in here has to be the same type, like all integers. And their size is fixed from the start. Now that sounds like a limitation, but it's actually their superpower. Because of that rule, NumPy can store all the data in one single, neat, continuous block of memory. No more jumping around.
And this is what you get for being strict. 125 times faster. I mean, let that sink in. We're not talking about a 10% or 20% improvement. On a big operation with a million items, NumPy is just in a completely different league. This is literally the difference between an operation finishing in 1 second versus you going to get a cup of coffee while you wait for the Python list to finish. It's a total game changer. So you might be asking, how is that even possible? Well, the secret is that contiguous memory we were just talking about. Because all the data is lined up in a neat row, NumPy can do something really clever. It completely bypasses Python's normal, slower way of doing things. Instead, it hands off the entire block of data to a super fast piece of code written in C that just rips through it at lightning speed. And there's another bonus. It works great with your CPU's cache. You can think of the cache as this tiny, ultra-fast desk right next to the processor. Since the data is all in one block, the CPU can grab a big chunk and put it on its desk to work on, instead of having to run back to the big, slow warehouse, your main memory, for every single piece of information. It's just incredibly efficient.
Okay, so now that we know why these arrays are so powerful, let's actually look under the hood. We're going to break down the core of NumPy, the end array, which just stands for n-dimensional array. Getting a handle on its basic properties, or attributes, is absolutely key. And to keep things simple and clear, we're going to use this one example for the next little bit. We'll just call it Array A. As you can see, it's a 2D array, pretty straightforward, 2 rows, 3 columns, all filled with integers. All right, so every single NumPy array comes with some built-in information about itself. Let's walk through the most important ones using our Array A. First up, we have .ndim. That just tells you the number of dimensions. Since Array A has rows and columns, that's 2 dimensions. Simple enough. Next, and this one is super important, is .shape. This gives you a little tuple that tells you the size of each dimension. So for us, that's 2, 3. 2 rows, 3 columns. You'll be looking at the shape all the time when you're coding.
Then you've got dot size. That's just the total number of elements in the whole thing. Here, it's 6, which is just 2 times 3. The dot type tells you what kind of data is inside. In this case, there's 64-bit integers. And finally, dot item size tells you how much memory each one of those elements takes up, which for 64-bit integer is 8 bytes.
Okay, enough theory. Let's get practical. We know what an array is, so now how do we actually make one? Let's go over some of the most common ways you'll be creating arrays.
So the most obvious way is just to take a regular Python list and convert it using np.array. But a lot of the time, you'll need to create arrays from scratch. For example, np.zeros and np.ones are perfect for when you need an array of a certain size, but you don't have the final data yet. You just create a placeholder of zeros or ones to fill in later. If you need a different placeholder value, you can use np.full to fill an array with, say, the number 99. And np.arrange is your go-to for creating a sequence of numbers. It works a lot like Python's range, but it gives you back a powerful NumPy array instead of a list.
Now, changing the shape of an array is something you'll do constantly. Here's a great example. We start with a simple, flat, one-dimensional array with numbers from 0 to 11. Then we use reshape. And here's the cool trick. That -1, what this does is it tells NumPy, hey, I want 3 rows, you figure out how many columns that should be. And NumPy automatically calculates that it needs to be 4 columns. It's such a handy little feature. It makes your code way more flexible because you don't have to hard code all the dimensions yourself.
Okay, we've been talking a lot about speed, speed, speed. Well, now it's time to pull back the curtain on the concept that makes it all happen. It's called vectorization, and it is the secret to NumPy's incredible performance.
So what exactly is vectorization? At its heart, it's a really simple idea. Instead of writing a for loop that works on one element at a time in Python, you perform the operation on the entire array all at once. Remember that r times 2 from earlier? That's vectorization in action. Because the data is all in one block, you can just hand the whole thing off to that fast C code we talked about and let it do its magic, completely avoiding the slow Python loop.
I love this analogy because it's just so perfect. A for loop in Python is like riding a bicycle. Yeah, you'll get there eventually, but it's one pedal stroke at a time. It's a lot of work. Vectorization with NumPy? That's the sports car. You're covering the same ground, but you're doing it with incredible speed and power, all in one go.
And vectorization has this amazing sidekick called broadcasting. Think of it like a smart, universal adapter for your arrays. It lets NumPy perform operations on arrays that don't have the same shape, which is a super common problem. So in this example, instead of you having to write a loop to add that 1D array to every single row of the 2D array, NumPy just figures it out. It virtually stretches the smaller array to match the bigger one and then does the math. The best part is, it does this super efficiently, behind the scenes, without actually making copies in memory. It's pure magic.
All right, we've covered a ton. The why, the what, the how. So let's bring it all home and talk about the simple, practical steps to get you up and running with NumPy yourself. And getting started is super simple. It's just 3 steps. First, pop open your terminal or command prompt and just type pip install NumPy. That's it. And hey, if you're using something like Anaconda, it's probably already in there for you. Second, whenever you start a new Python file, you just need to write that import line at the top. And finally, as a quick sanity check, just try printing the version. If a number shows up and you don't get an error, you are officially ready to go. Now, I really want to double-click on that import line, import NumPy as NP. Look, this isn't just a casual suggestion. It is the absolute universal standard. Every tutorial, every piece of documentation, every data scientist's code you'll ever read uses NP as the abbreviation. It's like a secret handshake for Python data people. Using it makes your code instantly familiar and professional. Just always do it. So when you boil it all down, NumPy is so much more than just another Python library. It's the bridge. It's what gives us the raw, blistering speed of a language like C, but wrapped in the friendly, readable syntax to Python. You get the best of both worlds, and that combination is precisely what powers modern data science. So the real question is, now that you know about it, what are you going to build with all that power?